Hi everyone. So in the previous video we studied about static fields. Now in this video we are going to study about time varying fields, but before that we will start studying about continuity equation. So this has nothing to do with the time varying fields, but this will be used in our analysis. That's why we are studying it. Okay. So let's understand the meaning of continuity equation. So what continuity equation shows? Continuity equation shows the continuity of a current. So let's understand that. What do I mean by that? So let's assume a particular volume. This is a volume V. Okay, somewhere I am just assuming a volume V. Now this volume V has some free charges. It has some free charges. These charges are inside the volume. Okay, these charges, let us say this is a bowl. Inside the bowl there are some charges. Inside the bowl there are some charges. Okay, now what will happen is that, and these are the charges, Q charges are there. Okay, I am calling it Q, and rho V is the volume charge density. That means per unit volume how many charges are there, per unit volume how many charges are there, and I am showing the charges by positive. Negative charge could also be there. Okay, now what is happening is that now these charges are flowing out of this particular volume. These charges are flowing out of this volume. So if charges are flowing, if with respect to time, if charges flows, what it will generate? It will generate a conduction current, right? With respect to time, if charges are flowing out of the volume, then it will generate some current. And one thing I hope you would be knowing, that positive charge will always flow in the direction of current and negative charge will always flow in the opposite direction of the current. Let's just say if current is in this direction, that means positive charge must be flowing in this direction and negative charge would be flowing in this direction. So if I am saying that positive charge is flowing out, positive charges are flowing out, that means current would have been certainly in this direction. Right, this would be the direction of current. So charges are flowing out, so these would be the direction of current. Now charges are flowing out, so in the volume charges are getting less. No, if charges are flowing out, that means in the volume charges are getting less, because charge is always conserved. We always know that charge will be conserved. So if some charge is getting less from here, that is going out. So if you are having some charges that is out of the volume, that means in the volume charges would have got less. So if charges are flowing out, that means charges would have got less. So dq by dt we will put a minus sign here, because charges is getting less. So that's why we are putting a minus sign. So IC is equals to minus dq by dt. Say yes or no. Okay. Now what I can write? What is my IC? J dot ds. What is JC? JC is your volume charge density. What I am saying, sorry, it is your volume current density, right? Or simply current density you can say, because surface current density we will not usually take in action. So simply current density I will call it. Here I am writing volume current density, but after this I will always take current density only. I will always call it current density. Okay, so JC dot ds I can write, and since it is a closed surface, so that's why I will put a close sign. Why it is a closed surface? Because you are enclosing a volume. If you are enclosing a volume, that means you must have used closed surfaces. 1 open surface, 2 open surface, 3 open surface, 4 open surface, 5th open surface, and 6 open surface. All these open surface combined made a closed surface which is enclosing a volume, right? So that's why I am putting a sign. IC equals to JC dot ds. This is pretty easy for you. This is pretty clear for you. From an open surface, how much current is passing? From an open surface, how much current is passing? So J is equals to di by dA. So from there I am writing I equals to J dot ds. And what about this? Minus d by dt. Can I write it down as rho v dv? Right? I can write it down as rho v dv. Because what is Q? What is rho v? Rho v is dq by dv. Per unit volume, how much charge is there? So what will be your Q? Rho v dv, right? Now I am writing this as it is. If I take this integration inside, if I take this differentiation inside, it will be converted into del. Why is that so? Why it will be converted into del? Look, this rho v could be a function of space as well. It could be a function of time as well. This rho v could be a function of space as well, it could be a function of time as well. But I am differentiating with respect to time only. I am differentiating with respect to time only. So I need to take space coordinate as constant. I need to take space coordinate as constant. So if one variable is taken as constant and other variable is being differentiated, so which kind of differentiation we will use? Partial differentiation. So that's why this has become del by del t. Outside it was d by dt, but if you are taking it inside, that means rho v could be a function of space and time, but you are differentiating with respect to time only, so that's why I am putting del by del t. So this is the integral form of your continuity equation. Continuity equation. Okay, this is the integral form. Integral form. Now what else we can do here? This can be written as del dot j dot dv. I should not say dot, del dot j dv, right? And this is minus del by del t rho v dv. So from here what you are getting? jc you can say, or direct j only you can say. So minus del rho v by del t. This is what you are getting. Okay, so this is also known as continuity equation. Okay, there is something known as, this will be used somewhere, that's why we are writing it, and there is something known as Ohm's law. So Ohm's law is J equals to sigma E. E, you know what is that? Electric field intensity. What is J? Current density. Current density or volume current density. From now onwards I will be only calling it current density only. So J is current density, E is the electric field intensity. What is sigma? Sigma is known as conductivity of a material. Conductivity of a material. What do you mean by conductivity? Conductivity is the ability of the current to flow. So in the material, if current can flow, then sigma will be non-zero. If sigma is 0, that means there are no free charges and current cannot flow. If sigma is 0, that means current cannot flow. In perfect insulator, insulator means there will be no current. In perfect insulator, sigma has to be 0. And if sigma is non-zero, that means from that material current can flow. Okay. So J equals to sigma E, this is known as Ohm's law. You must have studied in your elementary classes, but this is something that we are going to use. So till this point everything is clear. From this slide what you need to remember, del dot J is equals to minus del rho V by del T. This is one of the point, and J is equals to sigma E. You might not be able to remember it in the examination in a longer run, but you would be able to remember this thing. So in the examination you would be remember that, sir, I equal to dq by dt minus dq by dt, and this I can write J dot ds. From here I can get del dot J dv, and from here I can get minus d by dt rho v dv. So from there quickly you will be able to compare, right? Del dot J is equal to minus del by del t rho v. So very quickly you will be able to derive it in your examination. Now just for the fact only, okay, it will not be asked in the examination, but just for the fact, what does this equation represent? Changing charge with respect to time. Changing charge with respect to time generates a converging current. This is volume charge density, so I can call it charge only, right? I can call it charge. This is a charge density, this charge density, so kind of I can call it charge. So changing charge with respect to time generates a diverging current. The current could be diverging as well, diverging as well, or converging as well. It could be anything. Del dot J could be positive, then it would be diverging. If del dot J is negative, then it would be converging. If it is flowing out, diverging. If it is getting in, then it would be converging. So changing charge with respect to time generates a diverging current. This is what the equation represents. So if some equation is written, you should know what does it represent, not just the mathematical formula. You should be able to tell what it is representing. So changing charge with respect to time generates a diverging current. Now divergence can be positive as well, or negative as well, but this is what we can say, right? Now let's study about time varying fields. So that we are going to study using Faraday's law. In the previous slide everything is clear. Okay, yeah. So Faraday's law. So forget about the statement. Let's look at this diagram. So this is a closed circuit you are having. This is a closed circuit. This could be conducting as well, or it could be non-conducting as well. So let's consider it is a actual circuit. This is a closed circuit you are having. Okay, so although this circuit will not enclose any surface, this will enclose some surface area, but this is not solid here. Just you need to consider it is a closed line. This is a closed line circuit. Okay, this is a closed line circuit. Now I am having a magnet here. So let's see this analogy. So this is the closed line circuit. Only understand this part. Okay, I am having a magnet here, and this is a closed line circuit. Now if I move this magnet towards this particular closed line, if I am moving this magnet towards this surface area, then what will happen? These magnetic field lines are getting increased, right? Magnetic field is getting changed. If my magnet was here, then magnetic field was something else. If I move it towards it, then what will happen? Magnetic field will change towards this, from this particular circuit, from this particular closed circuit, the magnetic field will change. Do you agree to this point? If I take it near, magnetic field will change. If I take it away from it, then also magnetic field will change. And from a closed circuit, if magnetic field is changing, it will generate an EMF, and that EMF is equals to the changing magnetic flux with respect to time. This is what Faraday said. Through a closed surface, through a closed circuit, if the magnetic flux is changing, then it will induce an EMF. What do you mean by EMF? EMF, for now you will consider it as a voltage only. EMF means it will generate some voltages. If you are moving a magnet, or if anyhow the magnetic field is getting changed across this closed circuit, then it will induce an EMF. EMF is nothing but voltage only. So it will generate some voltage, and that voltage will be equals to d by dt of magnetic flux. D by dt of magnetic flux means the change of magnetic flux with respect to time. So this is what Faraday said. Now this closed circuit could be an actual circuit as well, it could be a non-conducting circuit as well. Now what did Lenz said? So Lenz said that the induced EMF will always oppose its cause. What do you mean by that? So this is my closed circuit, okay. Now I am taking this magnet towards the closed circuit. So what will happen? The magnetic field will increase in this direction. This is the north pole. This is the north pole. So if I am taking it towards the closed circuit, so magnetic field will increase in this direction. So now what will happen is that it will generate some current in this loop. In this wire, it will generate some current. I am assuming it is a conducting wire. It is a conducting wire. So now this conducting wire will generate some current. Now it will generate the current in a manner that it will oppose its cause. Why this current is generated? Because magnetic field was getting increased in this direction. Now it will generate a current. Let's just say if it generates a current in this direction, or let's take it opposite. So if it generates the current in this direction, then what will happen? What will be the magnetic field? If current is generated in this direction, the magnetic field will be in this side only. So initially the current was getting increased in this direction. Now because of the current as well, magnetic field is getting increased only, because the direction is same. Are you getting this point? The magnetic field was getting increased in this direction because we are moving the magnet towards it. So magnetic field was getting increased in this direction. Now it will generate some current. If I assume that the current is being generated like this, so current is being generated like this, then what will be the direction of magnetic field? So the current is increasing the magnetic field, but no, it should oppose the magnetic field. That means it should flow opposite. So if it flows opposite, if it flows in this manner, then what will happen? If it is flowing in this manner, then magnetic field will be this side. If it is flowing in this manner, that means magnetic field is in this side. So because of this magnet, the magnetic field is getting increased here. But because of this current which is induced, this is your I induced. This is your I induced. Because of this induced current, the magnetic field is getting less because it is in the opposite direction. You see that current, this will be the magnetic field. So now this current is opposing the change. In this circuit, the magnetic field was getting changed. What was the issue? Why this current came? Because magnetic field was getting changed. And what was happening with magnetic field? Magnetic field was increasing. magnetic field was increasing. Now what is the job of this current? To decrease the magnetic field. Magnetic field was increasing in this direction. Now I need to decrease the magnetic field in this direction. Then what I should do? I should generate a magnetic field which is opposite to this magnetic field. Are you getting this point? The magnetic field was getting in this direction. The job of this current is to oppose this increase of magnetic field. So it should generate a increasing magnetic field but in the opposite direction of that. Then this magnetic field will decrease. So this is the I induced. So if current is going in this manner, then in the opposite direction magnetic field will come, right? Similarly, can you let me know what will be the direction here? What will be the current direction here? Now I am moving the magnet away. So let's just say initially the magnet was here, now I am moving the magnet away. So initially more electric field lines were passing. More magnetic field lines were passing, not electric field lines. More magnetic field lines were passing. Now what will happen? If we are moving it away, then less magnetic field lines will pass. If we are moving it away, then less magnetic field lines will pass. So in this direction, less magnetic field lines are passing. So in this direction, magnetic field is decreasing. In this direction, magnetic field is decreasing. Now what is the job of the current? In this direction, magnetic field is increasing. So the induced current will have the job that in this direction you should increase the magnetic field. Again I am repeating, in this direction magnetic field is decreasing. So what will be the job of induced current? The job of induced current is increase the magnetic field in this direction. Look, EMF will be generated by the change of magnetic field. It has nothing to do with increasing or decreasing. Even if the magnetic field is increasing or it is decreasing, the EMF will still be introduced or induced. If magnetic field increases, then also EMF will be there. If magnetic field decreases, then also EMF will be there. So now magnetic field is getting decreased. So if the magnetic field is getting decreased, then in which direction the current will flow? The job of current is to oppose the flow of current, to oppose the cause. Now why this current is flowing? Why the current is induced? The current is induced because in this direction magnetic field decreases. So now the job is to increase the current in this direction. So if you need now the job is to increase the magnetic field in this direction, not current, sorry, to increase the magnetic field in this direction. So in which direction current should flow? The current should flow like this so that the magnetic field increases. So the current should flow like this. If the current is flowing like this, then magnetic field will be in this direction. So magnetic field will increase. Is that clear to you or not? Let's repeat it again. I was taking this magnet, so magnetic field lines were getting increased in this direction. In this direction, magnetic field lines were getting increased. Now, an induced current will be there. The job of this induced current is to decrease the magnetic field in this direction. So now, where it should flow? It should flow in this direction so that in opposite direction magnetic field comes. So if in the opposite direction magnetic field is coming, then anyway it will be going down. You are having a force of 5 Newton here. If I apply the force of 3 Newton here, then the force will become 2 Newton only. Initially it was 5 Newton, it will become 2 Newton only. The same thing. Initially the magnetic field was increasing in this direction. Now what will happen? Because of this induced current, magnetic field will flow. Magnetic field will have some field lines in this direction as well. So anyway, in this direction magnetic field lines will decrease, right? Here similarly, we were going away. Here we were going away. So if we are going away, what does that mean? That in this direction magnetic field lines are getting decreased. In this direction magnetic field lines are getting decreased. So now what do I need to do? I need to introduce a current, or a current should be induced in a manner that in this direction magnetic field increases. So if I need to increase the magnetic field in this direction, then what should be the direction of current? This should be the direction of current. If this is the direction of current, then magnetic field will be flowing in this direction only. So it will increase the magnetic field. Well and good. Is that clear to you? Okay. So it is always opposing the flow. So that's why we write EMF equals to. So there will be a slight modification. Negative sign will come here. Okay. So minus d phi m by dt. Why this negative sign? because it is opposing its cause. So EMF will oppose its cause. So that's why we will put a negative sign. Okay, let's solve this numerical. This is a current carrying wire. It is a current carrying wire. Okay, current carrying wire. And these A and V are two conducting loops. Two conducting loops are there. So basically this is the wire. Okay, one conducting loop is somewhere here, another conducting loop is somewhere here. All are in the same plane. All are in the same plane. All are in the same plane. What is your question? The question is you need to show the problem. I did not even write. Show the direction of induced current. Okay. So try doing it on your own. Draw the direction anti-clockwise or clockwise, and then let's check back your solution, because there is very high chance that you will get it wrong. Okay, let's start now. So current is increasing in this direction, right? Sorry, current is decreasing in this direction. Current is decreasing in this direction. Because of the current, what will be the direction of magnetic field here? Current is like this. So direction of magnetic field will be coming towards you. So this will be the direction of magnetic field. And at this side, this is the current. So direction of magnetic field will be going in. This will be the direction of magnetic field. Again, I am showing this is my wire, this is my current. Direction of magnetic field will be like this. And at this point, direction of magnetic field will be going inward. I hope you remember this. This will be the direction of magnetic field. So at this point, it is coming towards me, and at that point, it is going in. Okay. Now, if current is decreasing, I hope you remember H is proportional to I, right? H equals to I upon 2 pi r. So same flux will also be proportional to I. So what you can say is that if in this direction current is decreasing, then in this direction magnetic field decreases. I am calling this as positive Z just to explain it, okay? And this I am calling as negative Z. This is what I will call. So let's talk about loop A now. So in loop A, in positive Z direction, the magnetic field decreases. Say yes or no? The current is decreasing in this direction. That means magnetic field will decrease in this direction. If this is the current, this is the direction of magnetic field. If towards me, the direction of magnetic field. If current is decreasing, that means magnetic field is also decreasing. So in plus Z direction, the magnetic field decreases. In plus Z direction, magnetic field decreases. So in what direction you want your induced magnetic field to be? Let's just say, if I say this is my I induced. If this is my I induced, then where it will generate the magnetic field? It will generate the magnetic field in this direction only. So in this direction, in plus Z direction, the magnetic field was decreasing. So what is my job? If in the plus Z direction, my magnetic field decreases, if in the plus Z direction, my magnetic field decreases, then the induced current should be flowing in a manner that in plus Z direction, your magnetic field should increase. In plus Z direction, if my magnetic field is decreasing, then induced current should be flowing in a manner that your magnetic field should increase. So if your magnetic field should increase, that means it should flow anti-clockwise. If it is flowing anti-clockwise, then in this direction only magnetic field component is coming, so it will increase the magnetic field. Is that clear to you or not? Did you understand what we are doing here? Look, it's what people will think is that, sir, okay, actual magnetic field is in this direction, the time varying magnetic field is in this direction, so induced magnetic field should be in the opposite direction. No, the magnetic field is decreasing. No, here what was happening in the second example, in this direction magnetic field was decreasing. In this direction magnetic field was decreasing. So if it was decreasing, then I induced was in such a manner that the magnetic field increases in this direction. So that's why I induced was flowing in this manner. So magnetic field was increasing in this direction. So here what is happening? in this direction magnetic field is decreasing. If magnetic field is decreasing, what is the job of I induced? To increase the magnetic field in this direction. So to increase the magnetic field in this direction, what should be the direction? This, so that the magnetic field comes towards me only. So what about this now? Because in this direction, going into the screen, in minus z direction, your current is getting decreased. So current should flow, so this current should flow, the I induced should flow in a manner that the magnetic field should go in only. So in minus z direction, your magnetic field is decreasing. So current should be induced in a manner that in minus z direction, your magnetic field should increase. Again I am repeating, in minus z direction, if your magnetic field is decreasing, then current should be induced in a manner that in minus z direction, magnetic field increases. So current should flow like this. So magnetic field in minus z direction should increase. So this was a very good question. Okay. So whatever that you want to write, you can write down on your notes only. But here I am writing this is magnetic field decreasing, and here also I will write magnetic field is decreasing. If it was increasing with time, if current was increasing, that means in this direction magnetic field would have increased. So then the answer would be opposite. So always you need to check whether it is increasing or decreasing. If my magnetic field is decreasing, then my magnetic field, because of the induced current, should be in the same direction only. And if my magnetic field is increasing, then the magnetic field, because of the induced current, should be in the opposite direction. Is that clear to you? So the bottom line is it should always oppose. Okay, so here also it is opposing. What is the cause of this induced current? The cause of this induced current is the changing magnetic field. And how the current is, how magnetic field is changing? The magnetic field is changing. For this loop, it is getting decreased in minus z direction. That's why it wants to increase the magnetic field in minus z direction. So current is flowing like this. And here it is opposite. Well and good. Let's see the next question. Before going to the next question, let's derive something. So EMF is equals to minus d phi by dt. Now this EMF, what did I tell you? It is like a voltage only. So this EMF is equals to closed line integration of E dot dl. Now how this formula came, you do not need to worry about that. You just remember only one thing, EMF is equals to closed line integration E dot dl. Will you be able to remember that? Yes. D by dt. Because I do not want to show you the complete derivation, because in the examination only you need to know the final result and what final result shows. So that also we will see what the final result is showing. But as of now, you just remember that EMF is given as closed line integration of E dot dl minus d by dt, and what will be your phi? Phi is B dot ds. So E dot dl. If I take this d by dt inside, what will I do? If I take this d by dt inside, what will I do? Del by del t, right? Why del by del t? Because b could be a function of x and t both. But I need to differentiate with respect to time only. That's why I need to take partial differentiation. Can I do it in this manner? Del cross E ds, right? And here what do I see? Okay, this is one of the form actually. This is also important result. Now I am just changing it. So what I am applying? I am applying the Stokes theorem. So E dot dl del cross E dot ds, and here what it would be. So what you are getting? What is V here? B is the magnetic flux. What is phi? I hope you remember it. B dot ds, right? This is magnetic flux density. Magnetic flux density dot ds. This is your phi. This we have already studied. So this I just replaced it here. So what you are getting here? Changing magnetic flux with respect to time. Changing magnetic flux with respect to time, what it will generate? It generates a changing electric field. Again I am saying, changing magnetic flux with respect to time generates a space varying electric field. Why I am saying space varying? Because what is del? Del by del x, del by del y, del by del z. So E has to be a function of space, no? If E is not a function of space, then let's just say E is something 2ax cap. If it is not even a function of space, then what will be the answer of del cross E? 0. Then del B by del T is also 0. That means B is not changing with respect to time. But if B is changing with respect to time, that means del by del T is finite. If del by del T is finite, that means del cross E is finite. If del cross E is finite, that means E has to be a function of space. Is that clear to you? Again, I am repeating. Del B by del T is finite, that means del cross E is finite. If del cross E is finite, that means E has to be a function of space. So what I am saying, the changing magnetic field with respect to time generates a space varying electric field. Is that statement clear to you? This is what this equation is representing. This is known as Faraday's law. Okay, this is known as Faraday's law, and this is our Maxwell equation as well, that we will write down. Eventually we are going to write it down, but for now forget about Maxwell equations. Just understand what this equation represents, because these will be highly used in our EM wave. So changing magnetic field with respect to time generates a space varying electric field. And what will be the direction of that electric field? So that I will tell when I teach you EM wave. Okay, what will be the direction of that electric field? By the way, here only you can see del cross E. What is the direction of del cross E? Certainly the direction of del cross E will be perpendicular to E, right? Cross product, right? So direction of del cross E will be certainly perpendicular to E. A cross B is equals to AB some magnitude sin theta n cap. So n cap is perpendicular to both A and B as well. So similarly, del cross E, whatever the answer you get, there will be some direction as well. So direction will be certainly perpendicular to E vector. Yeah, sorry for the interruption. So what I was saying, so what is the direction of del cross E? N cap. So n cap is perpendicular to E vector, right? N cap is perpendicular to E vector. So del B by del T is perpendicular to E vector. Del cross E is written as minus d by dt B. So what did you get to know? E and B are perpendicular to each other, because result of cross product will be in the direction perpendicular to E. Result of cross product will be in the direction perpendicular to E. So E and B are perpendicular to each other. So changing magnetic field with respect to time will be orthogonal to E, and same goes for other case as well. So E and B will be orthogonal to each other, and that will generate a EM wave. So that we will discuss when we study EM wave. As of now, you just remember this thing. So there I will again pick up this equation, and then I will discuss it, that both will be perpendicular. So if E is like this, then B will be like this. Okay, so that diagram we will make. But as of now, again I am repeating the statement: changing magnetic field with respect to time generate a space varying electric field. Is that clear to you? For static case, okay, in the next page we will write down the conclusion. So for static case, what did we study? Del cross E is 0. So in that case, there was nothing varying, there was no time varying. The magnetic field was not time varying. But here, if the magnetic field changes with respect to time, it will generate some EMF, and because of that EMF, you will have a electric field. Is that clear to you? So this was the static case, and this is the time varying case. So in the time varying case, del cross E is equals to minus del V by del T. So if you remember the statement in mind, this will be very easy for you to remember. Time varying magnetic field generates a space varying electric field, and direction are perpendicular to each other. Is that clear? Or how you can remember in the examination? One thing you will remember, that sir, EMF will be equals to minus d phi by dt. EMF will be E dot dl, sir, and this will be, sir, d by dt b dot ds, sir. Sir, this will be del cross E, sir, and this will be minus del V by del T. So very easy derivation is also there, right? Derivation is very easy, very straightforward. If you remember the first statement, then there is no one who can stop you to derive these equations. If you just remember the first statement, and how will you remember the first statement? Magnet, loop, EMF, d by dt. The magnetic field is getting changed. If you take the magnetic field is getting changed. So d phi by dt, EMF, that's it. So this is how you are going to remember the first statement. So that's why I am showing you all these things. It might be the case that these things will not be asked in your examination, but these will help you to remember the formulas in a longer run, and you will have the actual understanding of the formula, that what this formula is representing, right? So each formula has its own significance, so that we should understand. And this was the integral form, right? This was the integral form. So this is the integral form we have, right? So electrostatic fields are conservative in nature. Electrostatic fields, not electric fields. Electrostatic fields are conservative in nature. And time varying magnetic fields generate EMF, right? EMF is equals to minus d phi by dt. So time varying magnetic field generates EMF, and if there is a EMF, then certainly there will be an electric field. What do I mean by that? What did I tell you? EMF is like a voltage only, right? EMF is like a voltage. So do you remember this formula? E is equals to minus del V. So if there is a voltage, certainly there will be electric field. If there is a voltage, that means there will be charge. What is voltage? Voltage is associated with charge only, no? In network analysis, when we teach that this capacitor is getting some charge, that means capacitor is getting charge. If capacitor is getting charge, that means it is developing some voltage. So charge is there, that means voltage is there. If voltage is there, that means electric field is there. On the plate of capacitor, if you are having some charge, then certainly it is having some voltage, and if there is voltage, then certainly there will be an electric field. Okay, so in brief, let's discuss about the capacitor as well. If you do not know it, but in the basics of network analysis, we study all these things. So here I am discussing about the capacitor, because that will be used in our further analysis. So here only I am discussing it. This is the capacitor which is having a capacitance. What is the formula of capacitance, if anyone knows? Epsilon A by D, where what is A? A is the cross-section area of these plates. A is the cross-section area of these plates. These plates are shown by a line, but these are actually having some cross-section area. So A is the cross-section area of these plates. What is D? D is the distance between these two plates. That is D. So capacitance is given by epsilon A by D. Is that clear to you? What is epsilon? You know. What is A? You know. What is D? You know. Right? What else I can teach? This is also, that will also be used. So let's just say if this plate is charged with positive charge and this is charged with negative charge. Okay. Anyhow, on this plate you are having positive charge, on this plate you are having negative charge. So if here you are having positive charge and here you are having negative charge, that means there will be an electric field. So from positive charge, electric field lines go out, and in negative charge, electric field lines come in. So that means from here to here there will be electric field. So this will be the direction of electric field. If one plate of the capacitor is positively charged, other plate is negatively charged, so there will be electric field which will be coming from plus to minus, plus to minus. So only these things you need to remember. Okay, just I wanted to discuss because these will be used when we study about displacement current. So next we are going to study about displacement current only, so there it will be used. So that's why I am dealing it here. Okay, only these things you need to remember. E is equals to epsilon A by D. A is the cross section area, D is the distance between them, epsilon you already know, which is permittivity, and if it is positively charged, it is negatively charged, so there will be an electric field. Is that clear to you? Okay. So let's see this question. Vector potential of magnetic field. I did not teach you about that, right? What is vector potential? So you cannot solve this problem. So first let's understand what is the vector potential of magnetic field. So what did you study? We know that del dot B is equals to 0. That means divergence, or I will write just divergence of B is 0. What are your null identities? CG is equals to 0 and DC equals to 0. So curl of gradient is 0, divergence of curl is 0. Divergence of curl is 0. Again I am repeating, divergence of curl is 0. So B has to be curl of something. When I said del cross E is equals to 0, so there what did I write? E is equals to minus del V, right? So similarly, if I am saying that divergence of B is 0, divergence of B is 0, so divergence of some curl is 0, so B has to be curl of something, right? If del cross E was 0, so E was minus del V, so B is del cross A, and this A is your vector potential of magnetic field. Okay, Now you can try this question. Try solving this question on your own now. B is equals to del cross A. This formula you understood. How this formula came? So from an analogy you will be able to remember that you know that del cross E is equals to 0 for static case. So from there what did I write? That my यार ये E को ऐसे लिखने की आदत मेरी जाएगी नहीं. E is equals to minus del V. Not sorry. V is not your vector quantity. V is not a vector quantity, so minus del V. So similarly, here what I am using, divergence of curl is equals to 0. So divergence of curl is equals to 0, B is equals to del cross A. Now you can try this question on your own. You need to find electric field. What do you know? That time varying magnetic field generates electric field, right? But there is a negative sign. Don't forget this negative sign. There is a negative sign as well. Okay, time varying magnetic field generates a space varying electric field. Will you be able to remember it? Yes, I hope you will be able to remember it. And for this line integral form, you can remember EMF is equals to d phi by dt. So within seconds you will be able to derive it. Okay, so this you will be able to remember. Del cross is equals to minus del v by del t. From here what you can write? Del cross is equals to minus d by dt del cross A. Now what is this del? Del is a operator. Del cross A, del is a operator. So del is a operator. So d by dt is also an operator. So I can take d by dt inside. This A is a function, no? This A is a function. Del is an operator, d by dt is also dou by dt. I should not say d by dt. Dou by dt is also an operator. So I can take dou by dt inside. Say yes or no? Yes, certainly I can take. So del cross E. Why don't we write a vector sign here? Because del is an operator. It is not a quantity. If it was a quantity, we would put a vector sign. And if it was a quantity, then you could not take del by del t inside. But it is not a quantity. It is an operator, right? So here del cross minus sign will be there anyway. So what I am doing, del cross minus del A by del t. So if you compare both sides, what do you get? There you go. So no calculation, nothing. One formula you derived, which you do not need to remember. You are not going to remember this formula, but in the examination you should have the aptitude of solving these kind of problems. So if you have a clear mindset that they are relating it with magnetic field. So if they are relating it with magnetic field, vector potential. Okay, vector potential is time varying. That means magnetic field also be time varying. Magnetic field is time varying because del cross A. So this operator will be only on space coordinate. This can change your space coordinate, del by del x, del by del y, del by del z. But this cannot change the time component. So t will always be there in the final output. So if my vector potential is time varying, then certainly my magnetic field is also time varying. Or I should say magnetic flux. I should not call it magnetic field. I should say magnetic flux density. So my magnetic flux density is also time varying. If my magnetic flux density is time varying, that means it will generate a space varying electric field. So if you have these statements clear in your mind, then quickly you will be able to write down your equation. Otherwise you will think, sir, what is Maxwell equation? What is that formula? What is this formula? Nothing is formula, nothing like that. You should have the statements clear in your mind. So if those statements are clear, then you will be able to write down these formulas and quickly you will be able to compare, and this is the answer. Right? So what you are going to get? E is equals to 14t, right? No, minus 14t. Minus sign is there, one minus sign is there, one minus sign would be there. So 14t. And E I am asking at 3 seconds. So that will be 12. What is the unit of electric field? That is volt per meter, or it is different units are there, volt per meter. Okay. Is 42 volt per meter. This is as a unit, volt per meter. How it is coming? So from that as well I also remembered a good thing. So that also I am going to write. So I told you there will be electric field. So what this electric field will be equals to? E equals to V by D. Okay. V is the potential difference across the plates. V is the potential difference across the plate, D is the distance between them. So this electric field is equals to V by D. From here you can get the unit as well, volt per meter. Volt per meter. So what did I tell you? On the capacitor, positive charge will be there, negative charge will be there. In between there will be electric field. That electric field will be equals to the potential difference divided by D. So V is the potential difference. V is the potential difference on the plates. So in the capacitor you need to remember these things. V is the potential difference on the plate. So these will be used when we study the next topic. So in this lecture only we are going to study the next topic. So we will take a break, then we can study the next topic. So that is the inconsistency of Ampere's law. So let's take a break, drink some water. You can also do the same, and then we will start the inconsistency of Ampere's law. Meantime, let's do the revision what we have studied till now. So what we studied, continuity equation, del dot J equals to minus the dou rho V by dou T. Sir, you said that it will be used, but till now it is not used. Now it will be used. Okay, in the Ampere's law, in the inconsistency of Ampere's law, it will be used there. So there we are going to use this equation. So that this equation we studied, J equals to sigma E. This we studied. Then we saw that magnet closed loop changing, then it will induce the current. It will induce an EMF. EMF is d phi by dt. But there will be a negative sign because it will oppose its cause. What is the cause? It is getting increased or decreased. Based on that, you will see the direction of current, right? And then from there, we derive this formula. This formula has a very important statement. The changing magnetic field with respect to time will generate a space varying electric field. Okay, then this is the case of static, this is the case of time varying. So what is the conclusion? Electrostatic fields are conservative in nature, but time varying magnetic field will generate some EMF, and if there is some EMF, then certainly there will be electric field. EMF is like a potential only, so E is equals to minus del V. So if there is V, then certainly there will be electric field as well. Is that clear? And then we saw this thing, which is capacitor, epsilon A by D, positive charge, negative charge, electric field will be there, E equals to V by D. Vector potential of a magnetic field is given as this. So what will be the electric field at a particular time? So this vector potential of magnetic field is given. So what do we know? Del dot B is equals to 0. So from there B will be curl of some vector. So that is known as vector potential. So B will be curl of some vector, that is known as vector potential of magnetic field. So this I should have taught earlier, but in this problem only I taught it. Okay, this you should remember. Del dot B is equals to 0, then B is equals to del cross A. Analogy is the same. Del cross E is equals to 0, so E is equals to minus del B. So A is the vector potential of magnetic field. So del cross E is equals to minus del V by del T. So from there you get to know that your E is equals to minus del A by del T. So minus del A by del T 14T, and this is the answer. Well and good. Okay. Now we are going to study about the inconsistency of Ampere's law. So let me take a break and then we will start. Yeah, so let's start the second half of this video. So in this half we are going to study the Ampere's law. So what was your Ampere's law in integral form? That was H dot dl is equals to I enclosed. And in the point form it was equals to del cross H is equals to JC. Now this is not fully correct. What is the issue with that? So let's check that out. So what do we know? That divergence of curl is equals to 0. This null identity we have studied. Divergence of curl is 0. This is your curl. If I take the divergence of curl is equals to 0. So if I take the divergence here also I need to take the divergence. So divergence of curl is equals to 0, right? So your del dot JC should come out to be 0. But according to continuity equation, did we study continuity equation? Continuity equation. What continuity equation was saying? Del dot J was equals to minus dou rho V by dou T. Here del cross S was equals to JC. So what did I do? Divergence of curl is equals to 0. So I took the divergence on both of the side. If I take the divergence here, divergence of curl should be 0. Del dot JC should come out to be 0. But continuity equation says that del dot J should be equals to minus dou rho V by dou T. Here it is saying 0. Here it is saying minus dou rho V by dou T. So certainly there is some inconsistency in Ampere's law. So by equation 1 and 2, we can say that there is some inconsistency in Ampere's law. So what is that inconsistency? The del cross H is equals to JC. So only JC will not be there. There has to be some other term as well. Del cross H is equals to JC. So this is what he said. But there has to be some other term as well. That term I am calling as JD. I don't know what is that JD. I will find the value of that JD. But there has to be some other term as well. Because here we are getting to know that this is saying it is equals to 0. But it is not equals to 0. It is equals to some finite quantity. So there has to be some other term as well. So what I am saying is that let del cross H is equals to JC plus JD. I don't know what is JD. Okay. Now what I'm gonna do, again I'm gonna take the divergence on both of the side. So I know divergence of curl DC is equals to 0. So again del dot JC plus del dot JD. What is JD? I don't have, absolutely I have no idea. But can I tell one thing, that it will have the unit of current density, because this is your current density, right? This is your volume current density, or you can say conduction current density. Now volume drop, I will drop the word volume, current density only I will say. So this is your conduction current density, JC. JC is equals to sigma E. So if it is current density, then certainly this is also current density. So this has the unit of current density. Now del dot del cross H, del dot JC, del dot JD. This will be 0, and this is equals to minus del rho V by del T, or dou rho V by dou T, del dot JD. So what you are getting from here, the del dot JD is equals to, this is equation 1 I am calling, del dot JD is equals to minus del rho V by del T. But this is not what you require. What do you require? You require you require the value of JD, not del dot JD. So what you can do? Do you remember Gauss law? Do you remember Gauss law? So what is your rho V? Del dot D. Gauss law. Okay. Using Gauss's law, del dot D is equals to rho V. So what did you get to know here? Del dot JD is equals to, since this is also operator, this is also an operator. This is the operator on space. This is the operator on time. Both are different operators, so I can put this d by dt inside. So what I can do? Del dou by del t. What is JD? JD is minus sign, I cannot forget. Oh sorry, here minus sign will not come, no. This will go that side, so minus sign will be cancelled, no. Minus sign will be cancelled. That's what I was thinking. So what you are getting? Now this has a term, this is known as displacement current density. Okay, so value of JD is coming out to be del dou by del T. So what is this? Displacement current density. So from here, what is the value of del cross H you are getting? So initially, del cross H. So initially what Ampere said, del cross H should be equals to JC. But now after the modification, what did we get to know? That it is equals to JC plus JD. It is equals to JC plus JD, where JC is the conduction current density. Conduction current density, and JD is known as D small, displacement current density. Right? So this is your del cross H. JC is sigma E, and what is your JD? That is del dou by del T. So let's analyze this JD again. What is your JD? L over del T. So what it is saying? Can I write D as epsilon E? And if I say that epsilon is not a function of time, then can I take epsilon outward? I am saying that epsilon is not a function of time. This is what I am considering, that epsilon is not a function of time. If it is not a function of time, then I can take epsilon outward. So what is my JD? So a changing electric field with respect to time will generate some current, and that current will generate an magnetic field. And changing electric field with respect to time, a changing electric field with respect to time will generate displacement current density. This is displacement current density, or for now I am saying it as a current only, because what is density? I into A. This is some displacement current into some surface area. So for now, just for the statement, I am saying that changing electric field with respect to time will generate some displacement current, and that current will generate some magnetic field. So on a top level, what I can say, that changing electric field with respect to time will generate some magnetic field. Is that statement correct? So from here, finally what I am writing is that I am writing in this manner, that my del cross H is equals to sigma E plus, this was your static electric field. So because of the static electric field, you are having some magnetic field. But now if the electric field is changing, then also it will generate some magnetic field. Let's just say my conductivity is 0. If my conductivity is 0, then you would expect that your current should be 0. Sorry, your magnetic field should be 0. If your conductivity is 0, you would expect your current is 0. And if your current is 0, then magnetic field will also be 0. What do I mean by that? This was a current carrying wire, right? This was a current carrying wire. So if this was a current carrying wire, then it was generating some magnetic field. So if there is current, then certainly there will be a magnetic field. This was a current carrying wire. If there is current, then there will be a magnetic field. If sigma is 0, then current will be 0. And if we feel like that, if there is no conduction current, then we thought that the magnetic field should be 0. But even if sigma is 0, but electric field is changing, then certainly it will generate some space varying magnetic field. Is that statement clear to you? In the first half of this video, what did we study? Del cross E is equals to minus del B by del T. So there what was happening? The changing magnetic field with respect to time was generating some EMF. And if there isn't some EMF, then certainly there will be some electric field. Again I am saying, changing magnetic field with respect to time was generating some EMF. Changing magnetic field, this was the loop. Magnetic field was getting changed. So it was generating some EMF. If some EMF was being generated, that means certainly electric field is generated. Here what is happening? If electric field is getting changed, then there will be a current component which is known as displacement current. We will study about this displacement current in a very good manner, because question has been asked on this particular topic. So that we will study. So if there is a changing electric field, then certainly there will be a conduction, there will be some displacement current, and because of that displacement current, there will be a magnetic field. Is that statement clear to you? Okay, so this is what this equation represents. So this is known as modified Ampere's law. You should not remember this answer, you should remember this answer, or you can remember this answer as well. But you should know the formula. JC formula is sigma E and JD formula is del rho by del T. So any of these answers you can remember. And these answers are known as modified Ampere's law. Modified Ampere's law. So there was an inconsistency in Ampere's law which has been modified. That even if your conduction current is 0, then there will be one more component which is known as displacement current. We will study about it more. But when displacement current will be coming in action? When they reach changing electric field. Is that correct? Displacement current will be there. Displacement current will be there only when there is some changing electric field. Because if dou E by dou t, if del E by del t, or you can say d by dt is 0, if changing in place of changing, I should write time varying, right? Time varying. Okay, because changing can be taken as a space coordinate as well, that electric field is changing with respect to space coordinates, but time varying. Okay, so if there is some time varying electric field, time varying I should write, but there is no space. If there is some time varying electric field, so if there is some time varying electric field, that will generate a displacement current, and because of that displacement current there will be some magnetic field generated. Is that clear to you? Okay, so we will write down all these summary. Certainly we will write it down, but let's discuss about this displacement current more. We will discuss about this more, but when it will come in action? When there is a changing electric field. Okay, if electric field is constant with respect to time, then this component will be 0. If this component is 0, then JD will be 0. So if displacement current density is 0, then there is no displacement current, right? So this is a summary. For static case, what did you study? That H dot dl is equals to only IC, but H dot dl is equals to IC as well plus ID as well. There will not be only conduction current, there will be displacement current as well. Okay, so this is known as displacement current, and this is known as conduction current. Del cross is equal to JC plus JD sigma E del dou D by dou T, and these expression we have already written. Here I am not taking epsilon outward, because it's not necessary that epsilon is not a function of time. We will see the type of mediums. So there will be one type of medium where epsilon is function of time as well. So epsilon can be function of time as well. But here as of now, just for the sake of statement, we are taking epsilon not a function of time. In 99% of the cases, epsilon will never be a function of time. So that's why I am taking it outward. Okay, and let's see one more thing here. So this was your density, right? This is your density, and this is also your density only. This is displacement current density, this is conduction current density, right? So what will be your conduction current into cross section area? This is A shows area. Okay, this shows area. And what will be your ID? ID will be dou by dou t can be replaced with j omega. When we study EM wave, I will tell you why it can be replaced with j omega. For now, can you just remember this thing, or will you just believe me that dou by dou t can be replaced with j omega? Can you just believe me? Okay, so dou by dou t can be replaced with j omega. And what is your D? D is epsilon E. So this is constant, omega constant, E constant. So if IC and IE both are having the same electric field, if IC and ID both are having the same electric field, then ID will lead IC by 90 degree. Is that statement clear? Look, IC is, here I will write down again, IC is sigma EA and ID is j omega epsilon E. If this has a phase of 0 degree, so these will also have the phase of 0 degree, but J gives the phase of 90 degree. I hope you know this kind of basic thing. J will give a phase of 90 degree. So ID will have a phase of 90 degree. So ID will lead IC by 90 degree, but only when both have the same electric field. That means both are in the influence of same electric field, then only it will happen. Now, for this electric field is different, for this guy electric field is different, then you cannot say that both will lead by 90 degree. But if both are in the same electric field, if both are in the influence of same electric field, then certainly your ID, your displacement current will lead conduction current by 90 degree. So can I write down this statement? In the influence of in the influence of same electric field. Okay, even if you did not understand del by del t, how it is written j omega, then do not worry, we will discuss about it. Why it is becoming j omega and what is the meaning of j omega, that also we will discuss. Okay, meaning of omega also we will discuss. So for now you just understand that d by dt is giving me a phase shift of 90 degree. Can you just remember this thing? The d by dt will give me phase shift of 90 degree. So in the influence of same electric field, okay, a very important line, in the influence of same electric field, displacement current leads conduction current by 90 degree. माइक कनेक्टेड है यार, आवाज तो क्लियर आ रही होगी आपको. By 90 degree. Okay, now let's understand this conduction current more. Now we are going to discuss about conduction current, or we can say that the complete phenomena, whatever that we studied, that we are going to understand by a different analogy. So this is a capacitor you are having, okay, which is connected to a time varying voltage, time varying potential. Now tell me one thing, what is there between the plates of capacitor? Between the plates of capacitor there is some dielectric, and now you do not know what is dielectric. So just consider between the plates of capacitor there will be air. There will be nothing between the plates of capacitor. There will be air, right? This is one plate, this is the second plate. So between two plates of the capacitor there is air. So conductivity of air is 0. This will be air or free space. And now conductivity sigma of air is 0. If sigma of air is 0, then conduction current density will be 0, right? If conduction current density is 0, then conduction current should be 0. Conduction current is 0. So if we do not know all these things, if we don't know all these things, right? Forget about all these things. Inconsistency of Ampere's law, forget about that. If we do not know all these things, then what we would expect? That if I put a magnetic needle here, if current is 0, that means there will be no magnetic field. So if I put a magnetic needle here, then it should not move. I am repeating the statement. I do not know the inconsistency of Ampere's law. I only know that as per the Ampere's law, H dot dl is equals to IC. So if IC is 0, then certainly there should not be any magnetic field. If IC is 0, that means there should not be any magnetic field. So if I put a magnetic needle here, then it should not move. But when we did the experiment, then it was moving. So what did we get to know? That IC is 0 here, there is no doubt about that, because conductivity of air is 0. But certainly there is some other current component. And what is that current component? That current component is known as displacement current. So certainly there will be a current, displacement current. Now how that current came? This is the doubt. That why that current came? What is this? This potential. This potential is time varying, right? This potential is time varying. Now the same potential is applied across the capacitor as well. Same potential is applied across the capacitor as well. So across the capacitor as well there is time varying potential. Time varying potential means time varying charge. If I am saying that my capacitor is charged to 5 volt, so what is the charge on that? 5 by C. Q equals to CV. Very basic network analysis. Very basic network analysis I am asking. Q equals to CV, you know. If I am saying my capacitor is charged to 5 volt, then that means what is the charge on that? 5C. Sorry, 5C, not 5 by C, really sorry. So the charge on that is 5C, right? So if my voltage is varying, then certainly charge on the capacitor is also varying. Here the charge is also varying. Sometimes it is getting less. Let's just say it was some sinusoid. Voltage was some sinusoid. So charge will also be sinusoid. The charge is also varying. Now if charge is varying, then certainly electric field will also be varying. Because what is electric field? From Q some electric field lines will go out. So if this is the positive charge, this is the negative charge, so these will be your electric field lines, right? These will be your electric field lines. Now this charge is varying, so electric field lines are also varying. So if there is some varying electric field, so what that will generate? Displacement current. Is that clear to you or not? Again I am repeating everything that I have taught. What did we think? We do not know about inconsistency of Ampere's law. So what do we know? Between the plates of the capacitor there is some air. If there is some air, that means conductivity of that air is 0, so there will be no conduction current. If there is no conduction current, then as per the law we should think that there should be zero magnetic field. If there should be zero magnetic field, so if I put a magnet there, or if I put any magnetic needle there, so that magnet should not move. But when we did the experiment, we got to know that this needle is moving. Now if the needle is moving, then certainly there has to be some magnetic field. If there is some magnetic field, then certainly there has to be some current. So in the air there is some current. What that current is and how that current is coming, then we got to know that we have applied a vector, we have applied a potential here. That potential is time varying. If the potential is time varying, then certainly the charge on the capacitor is time varying. If the charge on the capacitor is time varying, that means the electric field is time varying. If the electric field is time varying, so the time varying electric field generates a current, and that current is inducing some, or that current is responsible for generating the magnetic field. Is that clear to you or not? Okay. Yeah. So this statement could be written here. I will write as per Ampere's law. As per Ampere's law. By the way, who did all these things? I did not do all these things. Okay. Maxwell did all these things. Not Glenn Maxwell, the guy who bashed Bangladesh. Sorry, not Bangladesh. The guy who bashed Afghanistan. Not that guy. Who did this thing? Maxwell. Okay. So I did not do all these things. If I had done all these things, then I would not be teaching you. Certainly I would be getting a Nobel Prize. But no, I did not do all these things. I am just teaching whatever that he has done. Yeah. So ID equals to, as per the Ampere's law, so certainly there has to be some current. Now what is the magnitude of that current? I need to find the magnitude of that current. So magnitude of that current is minus, sorry, not minus, del D by del T, del D by del T. That is the magnitude of that current. So can I write it down in this manner? Is there any doubt? No doubt. Sorry, really sorry. This was not the current, this was the current density, right? This was the current density. This was the current density. If this is the current density, then what will be the current? Into area? Into the cross section area of the plates. This was the current density, no? Here we found out this was the current density. For finding the current, we need to multiply with area as well. Here also I forgot to multiply with area. Okay, really sorry. Here also I forgot to multiply with area. So here I should also multiply with area. Okay. So you have to multiply with area as well. So I should not write cross product because people will get confused. So forget about the vector sign now. We are not calculating vector. I am interested only in magnitude. So we are finding what we are finding. We are finding the magnitude of the current that is flowing between the capacitor plate. So what did I say? D by dt can be replaced with j omega. Do you remember this thing? Yes. Are you going to argue about this? No. You are not going to argue about this. That sir, you will say that, okay sir, we believe you. Okay. Into A. J omega epsilon E into A. Is that clear? So ID. What did I teach you? E is equals to V by D. In the previous lecture, E is equals to V by D. So can I replace this? E is equals to V by D. E is equals to V by D. So J omega epsilon into A into V by D. Again, this is not cross product. This is E is equals to V by D. Is that clear to you? So ID is equals to J omega epsilon A by D into V. J omega. What is epsilon A by D? Capacitance. Capacitance into V. This is your ID. So what I am getting as ID? ID is equals to V by 1 by j omega c. This was your ID here. So 1 by j omega c. What I am doing is that V by 1 by j omega c. So this j omega c goes upward. So V into j omega c. So in network analysis, did you study this thing? That this is a capacitor. It is having some time varying voltage. So how would you write down the current? How would you write down the current? You would use to write down the current as V by impedance provided by the capacitance. What is the impedance provided by the capacitance? 1 by j omega c. This is how you would write down the current, right? So the current that you used to write, that was the displacement current of the capacitor. You thought it was the conduction current. No, that was the displacement current of the capacitor. Now where will that displacement current go? Between the plates there is some displacement current. So where that current will go? It has to flow through this wire only, no? This current has to flow this wire only. In the plates, this is the ID current. So that has to flow through wires only. So for the wire, it is conduction current. For the wires, it is conduction current, but in the air in between, for the capacitor, it is displacement current. So here, the conduction current of the wire is equal to the displacement current of the capacitor. But here, when you used to write down the formula in network analysis, at that time you were not told that it is displacement current. You thought that, sir, it is the normal current which we used to write voltage by impedance, right? Impedance provided by the capacitor is 1 by j omega c. So this is how you write down. This is how you used to write down the current. But now is that clear? That was that displacement current. Okay. So from a voltage source between the plates of the capacitor, actually the conductivity is 0. So you should think that, sir, this should not even allow the current. But why the current is flowing? The current is flowing because of the changing electric field. And why electric field is getting changed? Because it is a varying voltage source. If it is a varying voltage source, that means here the charge is getting varied. If the charge is getting varied, that means electric field is getting varied. And if electric field is getting varied, then this will be generated. Now some people will have a doubt that, sir, in that manner, then if I connect a DC, here, if I connect a DC voltage source here, this is DC, not time varying, this is DC, let's just say 5 volt, then there should be 0 current through the capacitor. Because 5 volt is applied, directly it will be applied, right? 5 volt will be directly applied. So there should be 0 current through the capacitor. But those who have studied network analysis from PrepFusion, from me, so there I told you, if capacitor is directly exposed to a voltage source, so the current there will be impulsive. So for a very minute time, there will be very high current and then it will be 0. So for a very minute time, current would come. So why that current is coming? So this V voltage will take some time to reach here, no? Initially the charge, here the charge was 0. So it is taking some time to reach. So electric field got changed here. Electric field got changed. Initially electric field was 0. Now immediately electric field got changed. So what happened here? Del D by del E by del T. In no time electric field got changed. So that will generate a impulsive current. Look, if you haven't studied network analysis, then you can skip this discussion. Do not worry about that. Those who have studied network analysis from a good resource where impulsive current was discussed, those guys only will be able to understand. So I discussed the impulsive current. There I did not teach you this displacement current and all these kind of things. But some guys will have a doubt that, sir, if it is a DC source, then immediately voltage is there. So there is no electric field. There is no change of electric field. So the current should be 0. Yes, current is 0. But for a very minute time, for 0 second of time, it took the time to reach from 0 to V. The capacitor voltage initially was 0, but it took some time to reach to voltage V. How much time it took? 0 second. 0 plus second it took. If it is taking 0 plus second of time, that means electric field is getting changed in 0 time. So that's why there was an impulsive current. After that, the current was 0. Is that clear to you? Say yes or no. Right? So there are a lot of things which I can teach, but let's stop here. Let's not go more into that. Okay, one more thing, one small thing I wanna teach. So let's say one more thing. Okay, those guys who haven't studied network analysis, they can skip this part. After studying the network analysis, you will be able to understand what I am teaching here. Okay. So when there was a DC source, like step function was applied here, 5 ut, when step function was there. So what did we say? Initially the current was 5 by R. Slowly the current was getting decreased. Slowly the capacitor was developing some voltage. Initially there was 0 voltage, then it develops 0.1 voltage, then it develops 1 voltage. So slowly it is developing some voltage, and then when it develops 5 voltage, when it has developed 5 voltage, so current here will be 0. If this current is 0, then certainly current here is also 0. So there will be 0 current through the capacitor. Now let's analyze this thing with respect to capacitor only. There what did I tell? That 0 voltage was there, so current was 5 by R. If this is having 0.1 voltage, so 5 minus 0.1, the current was 4.9 by R. Then the same current was flowing through the capacitor. Then what did I say? If it is charged to 1 volt, then current was 4 by R, and the same current is flowing through the capacitor. This is what I said. Now let's analyze it using the capacitor only. So what was happening across the capacitor? Here you are saying negative charge, here you are saying positive charge. So constantly capacitor is increasing its voltage. Capacitor is increasing its voltage constantly. Okay, capacitor is increasing its voltage constantly. So here the charge is getting changed. If the charge is getting changed, that means electric field is getting changed. And if the electric field is getting changed, that means it will drive some current. So it was driving that ID current. It was driving that displacement current. R and C were in series. R and C were in series. It was driving the displacement current. Since they were in series, so here also the current was same. But for the resistor, it was the conduction current. For the capacitor, it was the displacement current. In this case, conduction current and displacement current were same. Is that clear to you or not? What I said? Okay. Again, I will discuss it. What I am saying, capacitor was slowly building up the voltage. From 0 to 5 volt it was going. Initially it was 0. It is slowly building up the voltage. That means it is slowly building up the charge. If it is slowly building up the charge, that means it is slowly building up the electric field. So if electric field is slowly getting changed, then certainly there will be some conduction current. Now in the capacitor current, conduction current was flowing, but this conduction current has to flow through this wire, and this current has to flow through this resistor as well. So in the resistor, what did I say? Conduction current, sorry, displacement current, sorry, really sorry for the misconception. In the capacitor, displacement current was flowing. So this displacement current has to flow through this wire as well, and has to flow through here as well. So in the resistor as well, this displacement current was only flowing, but for the resistor we will call it conduction current, because in the resistor conduction current can flow. So here conduction current and displacement current was equal because both were in series. And when it reached the steady state, when it has reached the 5 voltage, so now the voltage is fixed. If the voltage is fixed, that means charge is fixed. If the charge is fixed, that means electric field is fixed. And if the electric field is fixed, that means current is 0. So that's why we say that at the steady state, capacitor will drive 0 ampere current. Is that clear to you or not? This is the reason. You cannot teach all these things in the network analysis, because if we teach network analysis, if I teach all these things in network analysis, then no one will study from me. But I can give the knowledge when I am teaching EMFT. So this is the core concept of the capacitor, that if the charge has been stable, that means electric field has been stable. If electric field has been stable, that means there will be no conduction current. Sorry, again I am saying conduction current. There will be no displacement current. If there is no displacement current, then certainly there will be no current through the resistor as well. Is that clear to you? Okay. So if the voltage across the capacitor is changing, then certainly it will drive some current, no matter whatever the case is. If voltage is changing, it will drive the current. Okay. So this was the one fruitful discussion. I hope you must have understood a lot of things. Okay. And those who haven't studied network analysis, and if you are having enough time for your examination, okay, what I am saying, if you are having enough time for your examination, and you must have covered network analysis from anywhere, but I would recommend cover it from PrepFusion as well. You will get a whole new approach of network analysis. I can write it on paper that kind of at least cover transient analysis. Okay, at least cover the transient analysis part. In network theorems, you can watch the reciprocity theorem, and maximum power transfer theorem. In Thevenin's theorem, I cannot bring anything new. In Norton theorem, I cannot bring anything new. All the teachers will teach the same, but here there is something different. You will certainly realize there is something different. And once you go to the transient analysis part, you will feel there are a lot of different things. Okay, you will actually feel the circuit, that how the things are happening in the circuit. And this was one of the things which I discussed based on that only. Okay, so I highly recommend. I am not saying that your teacher was not good. I am not saying that. I am just talking about my content, that in my content you will certainly find something new. So that may help you in the examination because the level of examination is getting up. Now I will show you this question has been asked in the gate examination. Okay, whatever that I taught here, that has been asked in the gate examination. I will show you that. Okay, like in this lecture only we will see that that particular question has been asked in the gate examination itself. Yeah, so I hope you must have understood about displacement current. Okay, so what is the important statement? What is the conclusion? That changing electric field generates displacement current. Changing means here time varying, and if there is some current, then certainly magnetic field will be generated. Is that clear to you? Basically, del cross H is equals to sigma E plus, or I would say JC plus JD. So this statement I have again and again told you. If there is some current, then certainly there will be magnetic field. Okay, and how this current is being generated? This was generated using the static field, and this is generated using time varying field, time varying electric field. So if there is time varying electric field, it will generate some displacement current, and that will generate space varying magnetic field. Is that clear to you? Okay. So let's see the summary. What did we study? First, let's talk about static fields. So if there is some current, there will be some magnetic field. What do I mean by that? This is a current carrying wire. If it is having some current I, so there will be magnetic field. Okay. So if there is some current, there will be magnetic field. In statics, what we studied, del cross S is equals to JC, right? And if there is some voltage, there will be some electric field, or what I can say, E is equals to minus del V, right? So if there is some voltage, then there will be some electric field. So E is equals to del V. How do you get it? Del cross E is equals to 0. So this we studied in statics. Right? If there is some voltage, if there is some potential difference, then certainly there will be an electric field. Now in time varying fields, what did we study? If your magnetic flux is changing with time, if it is a function of time, if your magnetic flux, this was your loop, and this was your magnet. So your magnetic flux was changing with time, then what it was generating? It was generating some EMF, or you can say voltage, and because of that EMF, you are having some electric field. So what did we write? Del cross E is equals to minus del V by del T. So changing magnetic field or changing magnetic flux will generate an EMF, and because of that EMF, you are having the electric field, because your EMF was equals to E dot dl. Is that clear to you? And now if this electric field is a function of time, then it generates a displacement current. This we just have studied. If this electric field or electric flux is a function of time, then it will generate a displacement current, and that current will generate a magnetic field. Current generates a magnetic field. If magnetic field is a function of time, it will generate a EMF, and that will generate a electric field. If electric field is a function of time, then it will generate a current, and that will generate magnetic field. It will keep on going in this manner. And welcome to EM wave. So from here, the concept of EM wave gets up. So that we will study in the next lecture or next to next lecture, because in the next lecture I will give you some prerequisites which you should be knowing. But from next to next lecture, we will start studying about EM wave. So from here only I will pick it up, that how EM wave is generated. Again, let's understand this graph or whatever you can say. If there is some current, then certainly there will be magnetic field. If magnetic field is a function of time, if magnetic field is changing with respect to time, I should not say function of time, I will write time varying, or I could have written function of time as well, but let's write time varying. A time varying magnetic field will generate some EMF, and because of that you will get a electric field. A time varying electric field, what was the example we took? Capacitor. A time varying electric field will generate a displacement current, and that will generate a magnetic field. So what did we study here? JC was there, but if electric field is changing, then it will generate electric field, or you can say electric flux density, better magnetic flux density, we can say magnetic flux density. Okay. So this we have studied in time varying form. Okay. Now let's write down the conclusion of Maxwell's equation. So this we have already seen for static field. All this we have seen. Now in time varying field, what is the change? In time varying field, the change is d dot ds q enclosed. These two are same only. There was no change in Gauss law. This was Gauss law only. Magnetic monopole doesn't exist. So there was no change in Gauss law, but there was a new law introduced, which is Faraday's law. So that is saying that time varying magnetic field generates a space varying electric field. And there was another term introduced here that is known as displacement current. So what that guy is saying, that if there is changing electric field, so that will generate a displacement current, and because of that magnetic field will also come in action. So there is displacement, there is conduction current density and displacement current density. So this is JD, displacement current density. So it is known as modified Ampere's law, which was modified by Maxwell. So all these equations are known as Maxwell's equation. Will you be able to keep that in mind? We have studied Maxwell's equation for more than, I guess, 3.5 hours. We have studied it for more than 3.5 hours, and I hope you know every single thing related to that. Each point is clear to you. So conceptual clarity is very important because the level of gate examination has gone up. Now I will show you the question which was asked in gate examination. I hope you will be able to solve. There is a follow-up question from that. What if R and C were connected in parallel? Answer this question. And let me tell you one thing. I'm not defaming anyone. Okay. My motive is not to defame anyone. But when this question came, all the coaching institute gave the wrong answer. All. Every single coaching institute. You can go to their previous year solution. Like, error may happen. I'm not saying they are weak or anything like that. There are brilliant teachers of EMFT. Whoever teach EMFT in this field, they are brilliant. Okay. Like, I learn from them only. Right. I also learn from textbook. This is that I am not only learning from them, but I also learn from textbook as well. But I learn from them only. I have been also their student. But this was given wrong by everyone. Now I have given you enough concept. I hope you will be able to tell the correct answer. So tell me the correct answer of this question. This came in GATE 2022. And what did I do? Because GATE 2022 was my attempt as well. So did I do that correctly in the examination? No. I did not even attempt it. So during my attempt, I attempted 64 question out of 65. Okay. 64 question out of 65 I attempted. Like, there was some tukka as well. Tukka means like blindly you are guessing. So there was some guesses as well. But I attempted 64 question. In this question, I did not take any guess because I was pretty sure that what I am thinking, that will be wrong. Okay. So I was pretty sure that what I am thinking, that will be wrong. So that's why I did not mark it. But later on, I realized this was a pretty easy question. So tell me what is the answer of that. R and C are connected in series. A. R and C are connected in series. And there is some current. There is some current which is flowing through the resistor. There is some current which is flowing through the resistor, which is 2 sine t plus pi by 2. So this current is 2 sine t plus pi by 2. What is the displacement current through the capacitor? Tell me. What will be the displacement current through the capacitor? It has to be same, right? In series, resistance is connected, capacitor is connected. The current has to be same. That's it. This is the answer. Without even using the pen, you should tell the answer. Look, conduction current through the capacitor is 0. Conduction current through the capacitor is 0. Conduction current cannot flow because here sigma is 0. But there will be displacement current. Certainly there will be displacement current. Why there will be displacement current? Why there will be displacement current? Because here current is varying. Which capacitor is fed with which current? Capacitor is fed with 2 sine t plus pi by 2 current, right? Capacitor is fed with this current. A capacitor is fed with this current, that means current is changing on the plates of the capacitor, and current, what is current? dq by dt. Then certainly charge is also changing on the plates of capacitor. Again I am repeating, on the plates of capacitor, capacitor is being fed with the changing current. The same thing was happening in this RC circuit as well. When there was a step input, initially the current was 5 by R, then all the time it was changing 4.9 by R, 4.8 by R, 4.7 by R. So capacitor was fed with the changing current. That means if it was fed with the changing current, that means voltage here was changing. Initially it was 0.1 voltage, then it went up to 0.3, then it went up to 0.3, then 0.4, 0.5. So if current is changing, then certainly voltage is also changing. Because for capacitor, what is the equation? IC equals to C dVc by dt, right? So if IC is changing, then certainly VC will also change. So voltage is also changing, that means charge is also changing. If charge is changing, certainly electric field is also changing. So if there is electric field, then that means it will generate some current. So it is generating ID current, and that ID current will flow from the wire as well, and from the wire what current is flowing? 2 sin t plus pi by 2. So the current has to be 2 sin t plus pi by 2 only. Is that clear to you? Okay. In the next question, what will be the answer for the next question? This is R, this is C. Parallel, they are connected in parallel. Okay. And through the resistor, they are connected in parallel. Through the resistor, current is 2 sin t plus pi by 2. Through the resistor, current is 2 sin t plus pi by 2. Can you let me know, will both of them will have the same voltage? Because if two elements are connected in parallel, certainly they will have the same voltage. V is same. If V is same, that means electric field is same. Through the resistor, what current will flow? Conduction current is flow. J equals to sigma E. Through the capacitor, which current will flow? Displacement current will flow. What is that? Epsilon J omega E. E is same. If V is same, V in parallel, both will have the same potential. If V is same in parallel, V is same. If V is same, that means E is same. And if E is same, that means JD will lead JC by 90 degree. Look, epsilon is constant. This is constant. Omega is constant. Sigma is constant. Omega is here 1. Omega is constant. E is constant. Epsilon is constant. Sigma is constant. E is same for both of them. E means this capital E I am talking about. So for both of them, E is same, sigma is same, epsilon is same, omega is same. What does that mean? That displacement current will lead conduction current by 90 degree. So displacement current will lead conduction current by 90 degree. So what was your conduction current? That was T plus pi by 2. So it will have a phase of pi by 2 more. So what will be the answer? 2 sin T plus pi. Okay. So this will be your displacement current. So this was the case for parallel. This was the case for series. So this is the case for series. This is the case for parallel. So this was the answer given by most of the coaching institutes, and that I got to know in the examination that I am thinking this answer, that means this is the option, then it would be certainly wrong. That I knew. Okay, I knew that this answer will be certainly wrong, but I did not know what will be the correct answer. I did not think of all these things. In the examination, it is very tough to think about all these things. But that RC thing, that I explained here, you remember this thing, the RC thing, RC circuit thing, that RC circuit thing that I explained, that current is getting changed. So if I thought in that manner, then I would be able to solve this question in the examination as well. But it is very tough. But it was a 1 mark question, that's why I did not take any risk. And so this was the answer given, which was wrong. This was the correct answer, because both are connected in series. Capacitor will drive some conduction current. The conduction current will be same as the current that is flowing in the resistor. Here both are having the same potential, If both are having the same potential, electric field is same. If electric field is same, that means the displacement current will lead conduction current by 90 degree. So here it will have the phase of 90 degree. So this is the answer of B. This is the answer of A. Is that clear to you? Is Maxwell equations clear to you or not? So this is the end of Maxwell equations. I hope you enjoyed Maxwell's equation a lot, and if you enjoyed it, please do comment down and let everyone know that at least watch the second half of this video. The first half everyone would be knowing, like most of the teachers will teach the first half, but second half is very intuitive, like what actually happens in a capacitor, what is the actual property of a capacitor. So that you understood here, and this diagram was also important, that will be used in our EM wave. So that sets the base of EM wave. So there we will solve the Maxwell equation, and from Maxwell equation we will derive the expression of EM wave. So that we are not going to start in the next lecture. Before that, I need to give some prerequisites like types of medium, like what is sigma, like we will discuss about this conductivity and all these kind of things. Along with that, I will tell you what do you mean by time varying field, actual meaning of time varying field. Like if field is a function of space as well and time as well, then what do you mean by traveling in positive z direction, traveling in negative z direction. So those kind of prerequisites I will give you. Then we will start EM wave. Right. So I hope you are enjoying this lectures of EMFT. So till now we have covered the 20 hours of content, and in 20 hours of content I hope you must have understood a lot of new things, right? So let's meet in the next video. I will be expecting a lot of comments. So this is like a end of a chapter, Maxwell's equation. That was our chapter 2 which has ended. So I will be expecting a lot of comments from your side. Thank you very much.